Ready? I'm hoping you remembered everything we talked about on Wednesday, okay? The whole quantum number thing, the whole zip code thing, just to kind of remind you, and I might end up drawing this again, but maybe not, that in order to say where an electron is, you have to, and your homework's going to look like this. Okay, question mark electron, where is it? And you end up being, you know how like you have coordinates, like x, y coordinate? It's kind of like that, where you have n, a value for n, a value for L. Remember, that's your S, P, D, F thing. You have a value for your m sub L, and that's your, 0, plus or minus 1, plus or minus 2. That's the box. And then you have a value for your m sub S. Okay, so you need those four. They're actually numbers to say what's up with an electron. Okay, so then I kind of diverge a little bit. I'm going to focus just on two types of, well, more than two. Okay, so L's can be S, P, D, and F, and we said that corresponds to 0, 1, 2, and 3, right? So they have shapes. Remember that these are, I think of two things. I get so excited about it. They are actually where the electrons are at around the nucleus, and their location and their energy. So they're both of them. So the S's are spherical, and the P's are dumbbell shaped. And I have some figures to just kind of show you that. So starting with the S's, there's different ways to look at it. Okay, that little kind of hump right there is kind of showing you where the edge of the orbital is. Okay, and this is an S-type orbital. And notice that it's kind of, it has its concentration or the probability of finding an electron there actually kind of changes a little bit throughout. Okay, so there's an S. Here's S. This one right here, this middle one, is what is the probability of finding an electron at a given distance from the nucleus. If the nucleus is here going away, where are you going to find an electron? So this is S. So we said, and I'll just kind of remind you a little bit. So we had n is equal to 1, n is equal to 2. These are principal energy levels. N is equal to 3, And we said for each of these, you got an S-type, right? 1S. And we said at n is equal to 2, you pick up a P, right? N is equal to 3, you have an S. And then you pick up a D. N is equal to 4, you pick up an F. Okay, so the thing about it is right away you can see these S's are further from the nucleus and they have higher energy. Right, and that's kind of what this is showing you. Now onto a P-type. So P's are dumbbell shaped, okay, and dumbbell, barbell, I'm not sure really what that means, but they kind of are double lobed where the electrons are located. And at the center is the nucleus, and there's 0 probability of finding the electrons there if they are in a P-type orbital. I just think that is so cool. So when we get to P's, you guys told me the other day that we end up with 3 boxes. So S, P, D, and F. 1 box, 1 orbital. 3 orbitals, okay? And these are the 3 orbitals. Notice again at the origin, so we're talking X, Y, and Z coordinates here, which kind of hurts my brain. But at 0, 0, 0, that's the nucleus. And then we kind of have these double lobes coming out. This one actually is where I finish, and it kind of makes sense. So we have the PX, the PY, and the PZ. Okay, and so this is kind of fun. Look at this. PX, PY, PZ. They're degenerate, but they definitely have an orientation to them. I think that is so cool. So sticking with the P's, those are the the 3p subshells in n is equal to 2. So 2px, 2py, 2pz. If we put them all together, this is what they look like. Again, probability that the electrons in these degenerate orbitals are at the nucleus is 0. I just think that is so cool. But here they are kind of all. So you guys would hopefully tell me, I'm going to go ahead and use arrows for electrons. And I'll go ahead and fill each orbital with 2 electrons. Okay, 6 electrons there. Okay, if we had 6 electrons buzzing around in the 2p subshell, that's kind of the shape that they would make. All right, so spherical and dumbbell. Now beyond that, we don't have like a name necessarily to call them, but let's go up to the d orbitals. So for d, you guys would hopefully tell me 5. And here they are. And they hurt my brain. But I could take, and I'm not going to because I'm kind of impatient about that right now, but I could take each one of these little kind of labels underneath there. There's 1, 2, 3, 4, 5. They're just spatial representations of where the electrons are at in those 5 orbitals of a d-type subshell. Now remember, anything n is equal to 3 and above is going to have a d-type. Okay, so this just happens to be 3 or 3d. This is another representation of the 5 orbitals in the d-type subshell, specifically n is equal to 3 again. Okay. Can't remember. Oh, yeah. So let's kind of take a look kind of at the onion going up, kind of the lower energy increasing. So when n is equal to 1, we only have one type of subshell, 1s, and there's only one orbital. When n is equal to 2, we actually have 2 subshells, the 2s and the 2p. So this is kind of showing you where the electrons would be. N is equal to 3, we have 3s, 3p, and 3d. That's kind of what we got going on there. So I kind of told you, I do think that is so cool that in the dumbbell-shaped ones, the P ones, at the origin, 0, 0, 0, their probability of finding an electron is there is 0. So we kind of end up with these kind of nodal paths. So we have a nodal plane for this orbital here, a nodal plane there for that orbital, and a nodal plane there. That's hard to say for that orbital. And this one is nodal plane for one of the 5d orbitals. And then this kind of reminds me of kind of the old-timey wooden sort of ball and stick models that I've got here in the lab. But that is one of, I didn't even say anything about the F's yet, did I? So the F's need to have, of course, 7. Wait, yeah. My boxes get uglier and uglier sometimes. So one of the orbitals has that shape. You're like, well, what about the other 6? I don't know. Google it. Okay. So that's all shapes, kind of electron cloud shape, right? Now switching gears to that last quantum number. The last quantum number, the one we didn't talk about yet, but I've been alluding to it for a while now, is the spin. And there's only 2 possibilities, 2 values for the spin number. It can be plus 1/2 or minus 1/2. And I actually kind of went down to the nitty-gritty. We usually say that the plus 1/2 are the ones where you have drawn them with an up arrow. Okay, a minus 1/2 is where you have drawn them with a down arrow. Oh, catch up. I drew it here. It should show up there. Oh, I know. Because I don't know. up arrow, down arrow. Okay, that's what I tried to draw. So in these boxes, if you fill an orbital with 2 electrons, they have to have opposite spins. And actually, there's something called Hund's rule coming up. No, Pauli's exclusion principle, and that's part of Pauli's exclusion principle. So my video doesn't work, but I think that this figure does a pretty good job. When I look at this, I kind of think of, it looks like the blue Earth, and the blue Earth spinning on its axis of rotation, okay? And maybe you already know this, but if you have a planet like the Earth that has molten iron in its core, if you get that thing to spin, you get any charges to spin like molten iron, you actually create an electric field. And so that's kind of what we have going on at the subatomic particle level. Electrons are spinning. Now they can be spinning clockwise or counterclockwise. Clockwise or counterclockwise. And actually that's what you're representing when you do a +1/2 or a -1/2. Literally the direction of spin. And it's so cool. Things we take for granted, atoms we take for granted. But this is a part of an atom. This is electrons. And like this slide says, and I kind of looked it up a little bit because I always forget how this works, but if you have electrons that are paired like this, so any orbital can have 2 electrons, and I said if they have 2, one's up, one's down, the spins annihilate themselves, and that it makes it basically magnetically neutral. On Monday, we're actually going to be finding homes for electrons, and we're going to see that in some cases, and I don't care what subshell it's in, but in some cases, you just don't need homes for any more than 1 electron to be, okay, in an orbital. Even though it can hold 2, you don't need a second space. We call this unpaired. Okay, I think unpaired is mentioned here. Maybe not. If we have unpaired electrons, this actually can lead to, sounds fancy, paramagnetism. Paramagnetism, which means that actually that substance can be, it can be, a magnetic field can be induced upon it. Okay, that's paramagnetic. If I go ahead and fill an orbital, that's diamagnetic. I just think that's kind of cool, and they cancel each other out. Anyway, okay, enough about that. So again, kind of back to what we're going to do on Monday. We're going to find homes for electrons, and I'm going to point to this ordered quartet. Okay, you cannot have 2 electrons around the same atom that have identical set of 4 quantum numbers. They all will be unique. It will just happen. I'll kind of show you how that works. Okay, that's Pauli's exclusion principle. And I don't know if you buy this, but to me, let's see, I'll point to this guy right here, this diamagnetic pair of electrons. If I'm going to say nitty-gritty where those electrons are, check this out. They're going to have the same N, they'll have the same L, they'll be in the same box, that's the same M sub L, but what makes them unique is that one will be a +1/2 and one will be a -1/2. So Pauli's exclusion principle prevails if we add this 4th quantum number, which is actually the reality of it. Okay, so this just kind of wraps things up a little bit, just to kind of remind you one of the things we've been talking about is anytime you have an orbital, you can only have 2 electrons in it. It maxes out at 2. Okay, and if you have 2 in there, you have to be opposite spins. So if you're visually, you could show opposite spins by going 1/2 and -1/2, +1/2, -1/2, or you could do it visually by showing 1 up arrow and 1 down arrow. So again, in your homework, you're actually going to have to identify that if you have 1 orbital and they both have the same spin, that's a violation of Pauli's exclusion principle. That is not allowed in quantum mechanics. Not in this universe, anyway. Okay. So anyway, So just to kind of review how this works, all this is saying is if you you completely fill an S-type subshell, you have 2 electrons. If it's a P-type subshell, you have 6 electrons. If it's a D-type, since D's have 5 times 2 is 10. If it's an F-type, 7 boxes, 7 times 2 is 14. So those are kind of rules of subshells. Now, do we need to fill them up? Maybe not. Maybe not. And this kind of goes back to, remember we said that I'll kind of look at your quantum number here. We said that, not your quantum number, your angular momentum number, L, which is your subshell type. We said that L has values of 0, plus or minus 1, plus or minus 2, all the way up to, what, n minus 1. Sorry. Okay. So bottom line, if you know the value of L, here's the values of L, you know how many orbitals you have. So it's 2L plus 1. And you can put 2 electrons in each orbital, so the number of electrons your orbital accommodates, the number of electrons you accommodate is 2 times that quantity. So that's where those come from. And we said on Wednesday this kind of cool thing. Remember I kind of drew the onion and I said how many orbitals are in each n, principal energy level? And there's this cool algorithm. If you just take the principal energy level n and you square it, bada boom, it works out. But that's how many orbitals there are. Kind of hurts my brain to think why that is, but that's okay. Then if you are completely filling each of those orbitals, then the number of electrons you can accommodate is 2 times that. It all is a wonderful thing. So it seems like we already did this slide. Should I go backwards? Oh, this just kind of summarizes 3 general rules of exactly what we've been talking about with regard to electrons. A set of electrons around finding homes for sets of electrons. Electrons are located in orbitals. You can only put 2 electrons in each orbital, and they'll have opposite spins. Orbitals, we said, are grouped by subshells, SP and D type of subshells. And then subshells, we said, are further grouped into principal energy levels. So, all right. So then these will be due on Marvelous Monday. We'll take a quick look at these. I tried something, it seems kind of funny to me, but like on Twitter, actually just on TweetDeck, where I kind of send your Twitters out to you, you can delay a tweet. So I set a tweet to be delivered at 2:30, 2 tweets to be delivered. One is this assignment, and the other is the hints for this assignment. I thought that was kind of fun. So let's take a quick look. It's the little things. So those are like people get tweets like in the middle of the night, and you're like, I know that person wasn't up at that time. Well, you can delay it and send it anytime you want to. The things you can do. Technology. They look like this. And you may not probably need all of these hints. Sometimes they're a little bit over the top. So is this the first one, 77? Yep, oh, 57. Oh. Thanks. Let's grab the wrong one. There it is. These look better. So you may not need all these hints. Okay, select the correct answer and explain your reasoning. So your choices are A, B, C, and D. Which of them are correct if you have something that an electron n is equal to 3? And so again, my hints, I got carried away last year when I did these. So I don't know. I said when n is equal to 3, those boxes, those are your possibilities. And when n is equal to, for given the subshell, S, P, or D, then your M sub L value is set. We talked about M sub L values before. They're actually in purple up there. So I just kind of described it, and then we'll see which one fits most. I can't remember. Okay, so let's see. A, it said it must have a spin of +1/2. No, it can have -1/2. I don't know why so that one's not it. You're looking for the correct one. And so, I don't know. Just kind of look at my hints. Like I said, they may be over the top, kind of. The next one, write an acceptable value for each of the missing quantum numbers. Hence, there may be more than one option sometimes. You just have to write unacceptable value. Notice what we're doing in 58. What we're doing in 58 is kind of what I said over here. Narrowing down for a given electron, a set of quantum numbers. Yeah, got it. So again, those hints are out there, but you may not need to look at them. For what type of orbital is designated by these quantum numbers? And my little note to you, if you want it, is that stuff, that L stuff, I don't care. I don't need to know the specifics of the box. I just need to know the principal energy level and the L type in order to narrow it down to the, so this is your 1s, your 2s, 2p, 3s, 3p, 3d. This is all you need to know in the purple and the blue. 60, which of these are correct? If you're narrowed down to n is equal to 4, and you're narrowed down to m sub l is equal to 2. Well, if you're given m sub l is equal to 2, remember where that came from. It came from, it could have values of 0, plus or minus 1, plus or minus 2, all the way up to plus or minus l. So to me, that's a pretty high m sub l value. So it means you at least have 5. You at least have 5, if not greater. So see what my hints are. I guess that was my only hint. Concerning the electrons in the shells, subshells, and orbitals, how many can have? Oh, so like for instance, they kind of give you not all of the quantum numbers, but just kind of a scenario, and they ask you how many electrons can fit that bill. So those are my hints. There's still another one. That's okay, you got the whole weekend to do it. Concerning subshells and orbitals, and then we just had ask different questions about them. Now, did I already mention your Unit 4 exam in here on December 8th will have no calculators allowed, no calculators required. So it's all just concepts, which some of you will like, but some of you won't like. So these sort of kind of brain teaser questions, these are going to be some of what I'm going to ask you on your test. Kind of, can you know your way around quantum numbers? Okay, so that's, I think, it. Okay, and they should already be out there on Twitter.